All right, here we go. Lesson 6 for matrices. So in the final two lessons, for lessons 6 and 7, we're going to be looking at using an inverse matrix to solve a system of equations. We already have one method for solving a system of equations. That was Cramer's rule that we did in the last couple lessons. So the final stage of all this now is to use inverse matrices to solve a system of equations. So just a different method for solving a system of equations. In lesson 6, you're just going to be looking at how do you find an inverse, so that in lesson 7, we're going to see like the main purpose of it for solving a system of equations. So, but anyway, so first things first, something that we would call an identity matrix is one that would look like this, and that's where you get ones down the main diagonal and zeros everywhere else. So in a 2 by 2 matrix, it would look like this. In a 3 by 3 matrix, it would look like this. So I got the ones going down the main diagonal, everything else is a 0. The reason we mention this identity matrix is because if I were to multiply two matrices together, well, if they are inverses of each other, we get an identity matrix. You would have seen this within like basic fractions. So for example, if I had let's just say 2/3, right? What would we say is the inverse of 2/3? Well, if I flip it and call it 3/2, right? So if I multiply something by its inverse, what do we get out of that? Right? I would get 1, right? And so in terms of matrices, an identity matrix is like having a value of 1 for your matrix. So again, when I get those ones down the main diagonals and zeros everywhere else, that's like having a matrix value of 1. Same thing that you're seeing on this. So again, if I take a matrix, multiply it by its inverse, I get a value of 1, which looks something like this. So that's kind of where all this is headed here. So let me give you some examples of how this process works. So take a look at this. So if I have this matrix, we're calling this matrix A. So if I were to find its inverse, here's how the process goes. The symbol that we use to represent an inverse is the matrix title to the -1 power. So when you see this, that just represents that you're finding an inverse. So the general process of this, let me back up a little higher, there we go. The general process looks like this. So if here is matrix A, I'm going to take the determinant of matrix A, put that on bottom, and I'm going to multiply this times what I call the altered matrix. The altered matrix is where I take the downward diagonal and they trade places. So A and D will trade places. You can see that right here. C and B change signs. So if they're positive, they go to negative. If they're negative, they go to positive. And so you're seeing the opposite of C and the opposite of B right there. So I'm taking 1 over the determinant times the altered matrix, and that's going to create the inverse for me here. So if I were to do the determinant of this, which is AD minus CB, that's the number that's going to go on bottom. That's what you're seeing right here. And then again, I'll distribute it to this, and I'll create the inverse matrix. So let me show you one with real numbers here. So if I wanted the inverse of this matrix, again, I'm going to take the determinant, which would be -12 minus -8, and I'm going to put that on bottom of my fraction. So I have 1 over the determinant times my altered matrix. And so that's where these two guys trade places and these two guys change signs. So, and that's what you're seeing in this look right here. A little cleanup on this, and I get 1 over -4. All right, that's my 1 over my determinant. Here's the altered matrix. So if I distribute it -1/4 to all of those numbers, I get this. And this is now my inverse matrix. So if I were to multiply my inverse times the original, I would get the identity matrix that we discussed up above. And so that's just how this process works. And so that's kind of the main idea for today. So you can try one on your own here. I provided the answers so you can check and see if you're doing that right, if you want to give that a shot. But that's how that process works. So the only way we're going to use this for this lesson is going to be in a case that looks like this. So here's the original equation. I have a matrix times a variable equals this matrix, right? So A, X equals B. is our setup for this, right? And so that's what's being described right here. And so basically we are solving for x. We want to know if I were to multiply this matrix times what other matrix, I would get this result. So we're trying to find a matrix here. That's what x represents. It represents a matrix, and we're trying to figure out what that would be. So think about how you would solve just a general equation. I'm going to write this one down here. So I'll take you back to my example I had up above. If I had something like 2/3 x equals, let's just say 6. So if I was solving that equation, how would we do it? We would take the inverse of my fraction, and I would multiply it to both sides in order to get x by itself, right? That's how we solve for x. So I take the inverse, I multiply it over to the other side, because on the left side, these guys cancel. That's what we call the identity matrix. It's a value of 1. That's what gets x by itself. On the right side, I have the inverse times whatever was already there, right? And so if I multiply those two together, I would get 9, and that would be my answer for x. So we're doing the same process on this. And so the setup that you're seeing in the colored letters is super important, right? The original equation was ax equals b. That's what you see in red. In blue is what I need to do in order to get x by itself. So I need to find the inverse of a, multiply it times both sides of the equation in order to get x by itself, just like I did on this one, where I multiplied the inverse to both sides of the equation. So all this would start by figuring out what is the inverse of a. I'm then going to multiply it times b, and that will be my solution matrix for x. So doing the process that we did up above, I'm going to find the inverse of matrix A, which would be 1 over the determinant times the altered matrix. So if I did my determinant, which is what you're seeing right here, here's the altered matrix where the downwards change places, the upwards change signs, and I get the altered matrix. If I take my, this is just 1 over 1, if I distribute it to this, right, this is the result that I would get. So here's my inverse. So you can see up above, I'm multiplying the inverse to both sides of my original equation in order to get x by itself. Remember what happens on the left. If I multiply a matrix times its inverse, I get a value of 1. And so it's like having x by itself now. This is like having 1x on the left. On the right, I just have to multiply my inverse times the matrix B that was already there in order to get my solution matrix. And remember how we multiply these, right? I do a row times a column, right? That's something we covered in a previous lesson in order to get those solutions. Something that's super important that you have to remember on this, the order in which you multiply matters. So I need to, on the right side of this, I need to have my inverse first and matrix B second, right? That order has to stay in that way in order to get the correct solution when you multiply them. But that's it. That would be our solution for x on that. Let me show you one. We'll kind of work out one together in case you need to see one. You can always like pause and go ahead of me or something like that if you really want to. But this is a times x equals b. So again, my goal on this is to take the inverse of a, multiply it times matrix B in order to get my solution for x. So I first have to find the inverse of matrix A. So that's where I do my downwards, which would be 6, minus my upwards, which would be 4, which equals 2. So I'm going to do 1 over 2, 1 over the determinant. All right, so 1 over 2 times the altered matrix. So I already went through and just a second ago set up kind of the outline of what we're going to be looking at here. But if I took my altered matrix A here, so my -2 and -3 trade places. So -2 comes up, -3 goes down. My -1, -4 change signs. So +1, +4. So we're going to do, so if I distribute the 1/2, do notice that for a couple of these guys, it's going to create a fraction. And so we're trying to avoid working with fractions because I still have to multiply this inverse times matrix B in order to get my solution for x, right? Because here's the look. So one thing that you can do that would make things a little easier on the fraction work is save the fraction part till the end. So instead of distributing that to my altered matrix and then multiplying times b, I'm going to multiply this times b first, and then I'll bring in the 1/2 at the end, and that way I don't have to multiply with fractions at this part here. So let me kind of scroll over to the right. So for this matrix here, this is going to be, as I do my altered matrix times b, I'm going to get this guy, and then I'll deal with the 1/2 as my final move in order to get that last part here. So remember the usual multiplication here. If you did, your top row times your left column, you get the top left number, so on and so on. So as I would do something like 12 plus -28, I'll get that first answer. And so that's what we're filling in here on this part. So we'll just do that here real quick. So -16, oops, there we go, -16. Then if we did my top row times the right, so -18 plus 20. Bottom row times the left, so -6 plus 21. Would give us that guy. And then if I did my bottom row times the right, so 9 plus -15, gives us that guy. Now I can distribute in the 1/2 to get my solution. So now if I took half of -16, we got that guy, half of 2. Half times 15, we can just leave that as 15 over 2, or you could do it as a decimal, and then half of -6. And we have our solution for x. So always kind of a nice shortcut if you sort of recognize at this stage, instead of distributing and completing the inverse process, save that fraction until the end. And then, as you can see, that just made it a little simpler to do that final step.